Mm. Okay, so welcome everyone to the new Flower Monthly. This is the event, the monthly event we the Flower community meet together to hear the latest updates about Flower and also the latest projects that people from the community, like people like you, have built around Flower. So today is the 1st of October, first Wednesday of the month, and that's why we are here today. As usual, we're going to follow this agenda. First, I will give a brief update about things we have done in the Flower team. And then we will jump straight into two fantastic talks. One from Fran Cortés Delgado, he's from the University of Murcia in Spain. And the second one by Jiahang Li from Tianjin Normal University in China. Let's jump first into the Flower update. So as you have been hearing from us for a number of weeks now, we ran two events last week. But before talking about that, let me tell you about another very important update, which is the release of Flower 1.22. So it was only 2 weeks or so ago when we released Flower 1.21. With Flower 1.22, we don't have a lot of framework-related updates, but we have made a huge update to the documentation and other materials that make use of Flower. For example, the main tutorial in Flower, that is the tutorial you see at the beginning of the Flower docs, has been updated to the Message API. The Message API is now the best way to create Flower apps. It makes it so much more versatile to develop different types of applications. And now you are no longer restricted to the strict data structures used by NumPy client and all the strategies abstraction. So the main tutorial has been updated to reflect this new way of writing Flower apps. But worry not, there is also a migration guide that explains how to take your existing Flower apps into the Message API. It's fairly easy to do so. We follow that guide to also update the quick start tutorials for in the documentation. These are tutorials that are very simple and explain, for example, what the apps that you might create using Flower New actually do. These are very simple Flower apps for different type of frameworks like PyTorch, TensorFlow, JAX, MLX, and many more. We have also updated the how-to guides. These guides explain you, for example, how to save model checkpoints, how to make more effective use of the strategies, how to create the strategies from scratch, and many more. As I mentioned, we also updated all the Flower New templates to the Message API, including those for the Flower Tune LLM Leaderboard Challenge and for Flower Baselines. And also we have updated pretty much all the examples to the Message API. There are still 5 or so examples that need to be updated and will be updated in the coming days. You can read more about what the update was about in the release blog post that we put out early last week. And now, as you know, last week we were running 2 events in San Francisco. One was the Flower AI Day, where we invited big leaders from industry to speak about decentralized AI and some of them how they make use of Flower. I think this event was super successful and we'll have a lot to share in the coming days. Probably, without a doubt, the biggest announcement was the launch of the Supergrid. Essentially, the Supergrid is a service that runs Flower that makes it trivially easy to construct and manage your own federations. You can read more about it in the blog post that was released also last week before the Flower AI Day. And here I put some of the photos I took during the event. There will be more and probably some videos that we'll be sharing in the coming days and weeks. After that Flower AI event in San Francisco, we went to Stanford where we ran a super successful and I think amazing hackathon. Here there are also some pictures. There were almost 700 people registered. We had, in addition to people building their demos using Flower, there were 10 amazing lightning talks from folks that have been using Flower for research and also in production settings. It was an 8-hour hackathon. There were multiple tracks. Some people decided to follow one track that was more guided, where we had pre-partitioned some data set, some medical data set. People didn't have access to that data set, and the task was to enhance one Flower app that until you could get it to work with super good performance. Then you would take that model that was trained in Federation, and the people in the hackathon build some quite cool demos around it, like building a UI for doctors to use that model, and even embedding those models in an iOS app. This hackathon was very generously sponsored by AMD, so we were able to give some amazing prizes, including 2 pretty good AMD GPUs. And in addition, we had other type of prizes like Raspberry Pi clusters and many more. There will be a blog post coming out very soon with a summary of what the winners of the hackathon built during these 8 hours. And probably there will be some videos as well. So this is the Flower update. We released Flower 1.22. I encourage you to update and also to take a look at the new tutorials. And we ran 2 amazing events last week in the San Francisco area. And now, without further ado, let me introduce our first speaker. His name is Fran Cortés Delgado. He's from the University of Murcia in Spain, and he's going to tell us about his work using Flower in a talk titled Enriching Flower with Robust Aggregation and Security-Aware Extensions. Okay, Fran, the floor is yours.
Thank you. Thank you for having me. I'm going to share my screen. Okay, can you see my screen?
Yes, perfect.
Perfect. Well, first, thank you for having me here. I'm going to present my work, Enriching Flower with Robust Aggregation and Security-Aware Extensions. First, let me please briefly introduce myself. I'm Fran Cortés. I am an AI researcher from the University of Murcia, a city in the southeast of Spain. And well, this is the work that I have been doing, which is mainly enriching Flower in the European Reminder project. But what is Reminder? Reminder is a European project that will help privacy preserving federated learning for smart buildings. I will do just an overview of the architecture, but I'm not going to go deeply into it. But if you have questions later, you can ask, and I will be happy to answer. First, the architecture, what it does is protect and guarantee the privacy and the security of the data. Because despite the fact that most researchers think that federated learning is secure because you share your weights model, this is far from the reality because attackers can predict actually the data, the raw data from the weights. So what we do here is use some advanced encryption algorithms along with some robust aggregation functions and identification of malicious clients algorithms. So I will start first with this paper that we have published, which is a robust aggregation function. And for me, I think this is a quite out-of-the-box idea. It is based on the fast Fourier transform and is used to find the point where the density is condensed. And I don't know if you recall the fast Fourier transform from your time back at college, but it is helpful for going to the frequency domain where we can detect some outliers that we can remove entirely from the process of federated learning while maintaining the accuracy. Another thing that I wanted to comment, another paper that we have published is Flaegis, which is basically a detection of malicious clients through clustering. And this is quite interesting too, because it helps you to identify which are the malign clients and to remove them from the process before using the rows aggregation function. But let's see a little bit of data of our real results. And here we can see something pretty interesting, which is basically that using our rows aggregation function, you are going to maintain the accuracy despite the fact that we are increasing the percentage of malicious clients, as we can see in the purple line. The number are similar to the state of the art. Here we can also see some results of Flaegis, our other paper, which shows us if you noticed the blue lines, it is really good identifying the malicious clients among different attacks. Also, here if you notice the blue line, we maintain the accuracy while we increase the malicious clients using our approach Flaegis. So now I'm going to do an overview of the architecture, the real architecture, the architecture behind the project. So for that, I'm going to show a new ML and how we have enriched Flower through our new architecture. So if we go, we see it closer, we can see that the green boxes are the one that belong to Flower, and the blue ones are the new ones that we have added to enrich the framework. So if you see here, we have done some software design patterns as here for adding some clustering techniques, and also here we have add a mechanism to incorporate like new attackers to the process, and also we have added to a new strategy, the fast Fourier one that I explained before. So we wanted to not just stay just in the theoretical part, but also to do some kind of real work with real data here. So we published in Sino, you can access it, public access, some real data from the buildings where we work, actually work in Block A, and we have used our own IoT devices to obtain some data and also real public data from public stations. So the data that we are getting here are the temperature, the humidity, and why is this important? Because we can know the attacker could here know exactly when people are in the building, thanks to the temperature, humidity, CO2 stats. And that could be dangerous because the attacker could know when to rob our building, for instance. And also, what we wanted to do here, what someone could do, is try to predict the temperature. So before the workers arrive to their job, the temperature is settled to the one that normally they feel comfortable with. So we have secured this process. Some of the anecdotic data that we can see here, some results are here trying to predict the temperature in this federated learning scenario while also protecting it. So the proposal here for the next iteration and the proposal here for Flower here is enriching the Flower framework, extending it to simplify the integration of attacks using software design patterns. Um, Also adding the possibility of using clustering techniques and using our new aggregation function. So that's all. Thanks again. If you have any question, I will be happy to answer them.
Thank you, Francisco, for the presentation. I do have some questions, but before that, let me check if there are some in our, the platforms where we are streaming everything. Well, in the meantime, I'm gonna ask one, which is, I see in the last slide or second last slide, you have this base attack on the top right corner. Yes. No. Ne next one. Yeah, base attack. Can you explain how it works or what is maybe at a high level first? What does it do, and where does it connect with the rest of the system?
Really good question. Thank you for asking. Actually, this is for test a federated learning environment and see like stressed it with some attacks, and so we can see how it performs. So basically the base attack is just an abstract class which you can extend for implementing real attacks. For instance, widely known attacks from the literature could be min-max, lie, or label flipping, just or some data poisoning techniques too. It would help researchers to do this kind of attacks of federated learning scenario, which I think right now is not in the framework. So I think it could enrich the framework utilities.
Would just a follow-up question. Where does, for example, min-max attack uh, in interface with the rest of the system? Is it on the client side? Is it on the server side? Uh,
It is on the really good question again. This is on the client side. I mean, the client could perform as a good client, for saying that in a way, kind of send different weights um, to the server, so it low the performance of the model. So
mm,
this is our risk here, this kind of attack. But actually you could add new one. The good thing here also that I wanted to highlight is that you could extend this with as many attacks as you want, as you wanted. I just selected three, but you could actually use it with um, wherever you want.
okay, cool. Makes sense. Thank you for the answer. There is a question from Gonzalo Canovas. Um, Hello, Francisco Jose. Before asking my question, I would like to congratulate you on your interesting presentation. And
Thank you.
here's the question. I would like to know which design patterns have you used?
That's actually a good question. Thank you, Gonzalo. And the patterns that I have used here is the strategy pattern. I don't know if you're familiar with software patterns, but this is the one that I thought it was the more appropriate here, and it helps you just to implement some action that we want. In this case, the strategy would be um, an aggregation function, for instance, or attack function could be too. But I used here that pattern for the aggregation function. Thank you. Thanks a lot.
And there's another question from Alejandro Carmona. Um, you mentioned that you guys did utilize advanced encryption algorithms as well as robust aggregation functions and the Fourier transform. Can you delve deeper into which encryption algorithms were used and how?
Okay, thank you. That's indeed a good question too. Um, mm, I will use this slide for that. Well, regarding the advanced decryption, we thought about some homomorphic encryption algorithms, which is basically it is based on asymmetric encryption, which is RSA based algorithms with a public and private key. But the idea here is that you can operate with the encrypted data without losing information. So why is this important? Because if there is some man in the middle attack, for instance, someone who is spoofing our conversation and see the weights, it can in a way cipher, encrypt the weights. So it is not possible for the attacker to obtain information from the weights. So we thought about using homomorphic encryption, but we realized that we needed to operate with the weights because of how the aggregation function works. So what we did here was used instead of full homomorphic encryption, partial homomorphic encryption, which helps you to operate it with quicker, basically. And homomorphic encryption is is heavier, but also work for doing operation. So thank you again for the question.
Cool. I see Alejandro Carmona has the hand raised. I don't know if you want to ask something else live. Oh, you unraised it. So, okay, that's good. Eh, You can ask a question live if you want, but I think that's okay. Okay, I think if there are no more questions in the last 5 seconds, in the next 5 seconds, we can move on to our next speaker. Okay, thank you very much. Oh, please.
Thank
Okay,
you.
yeah,
Um,
Alejandro Cesar. Thank you for the answer.
we stop
Okay, well,
sharing.
thank you very much, Fran. I think that was super interesting presentation. For everyone else watching this stream, feel free to reach out to Fran if you have some questions about his research or if you want to collaborate with him in other projects. Now, let's jump to the next speaker. So the next speaker is Jiahang Li from Tianjin Normal University. Unfortunately, he cannot join us live now, but he spent quite some time preparing for his talk and he has pre-recorded it. So what I'm going to do is I'm going to play the recording he shared with us. And at the end of the recording, you will see that he already put some information on how you can reach out to him for questions about the topic he's going to present during his talk. And also if you want to, for example, check his papers and the code. So this talk is titled Federated Weakly Supervised Video Anomaly Detection from Jiahang Li. And I will play the video now. All right.
Hello, everyone. First of all, thanks for the invitation.
All right, let me just check the audio. Let's see. Mm. This is something I checked earlier on a different call and it was working. Oh, I see. Okay.
Okay. Page of the splitting enables effective
Can you hear it now?
multi-scene video and detection while ensuring data privacy. So let's dive in.
Okay, thank you. Then I'm gonna play it from here then.
Okay. My name is Jiahang Li. I'm currently an undergraduate at Tianjin Normal University, supervised by Professor Yun Su. My research interests include video and detection, weekly surprise learning, and real-world applications of federated learning. Okay. Video anomaly detection, or VAD, is about automatically finding unusual or abnormal events in video surveillance data. It plays a key role in improving safety and security for modern industries and smart cities. And here are some example datasets used for VAD tasks. This datasets predefine a set of abnormal events, such as driving a car on the sidewalk, stealing bike, and fighting, and other abnormal behaviors. If any frame contains one of these events, we consider that this frame to be anomalous. For VD tasks, we usually use a pre-trained feature extractor to extract video features as snippets, and these features along with video labels as inputs, and are used to train the model during inference. The model can detect normal events as 0 and abnormal events as 1. There are four main types of VD tasks. First, fully surprise VD use frame level labels during training, and one class VD training only on normal videos with no anomalies in the training set. And weekly supervised VD uses video level labels. If a video contains at least one abnormal frame, the entry video is labeled as anomalous. This is the unsupervised VD. The unsupervised VD does not use any label for training. To balance the performance and the labeling cost, our research focuses on weekly supervised VD. The first challenge relates to weekly supervised learning. In fact, weekly supervised VD can be viewed as a multiple instance learning problem. This is because during training, an abnormal video contains both normal and abnormal snippets. Sometimes even within the abnormal snippets, there may be both normal and abnormal events. Since multiple people in same frame may be doing different things, this complexity makes the problem even more challenging. To address this, previous methods typically use two types of loss function. A top key cross-interplay loss for abnormal video, and a center loss for normal videos. In this approach, abnormal videos are treated as positive bytes, while normal videos are treated as negative bytes. The top K highest scoring snippets in positive next are selected for the cross-entropy loss. Well, all snappies in negative bags are used for center loss. This helps the model learn to better distinguish between normal and abnormal behaviors. However, this approach mainly focuses on the top ranked data discrete snappies during training. Well, it is effective at identifying the most obvious abnormal snappies. It still has two main limitations. It may mistaken select the noise normal snappies as anomalous. It overlooks the lower ranked snappies that may still contain important abnormal events. You can see this two example. That's this one. Like this one. This is a normal snippet, but the previous method build this one as select this noise normal snippet as anomalous, and this one is abnormal snippet, but the previous method overlook this snippet. These limitations can lead to cumulative misclassification of normal snippets and missed distinction of significant anomalies during training, resulting in a higher false alarm rate. And to address this problem, we designed adaptive dynamic recursive mapping. Our approach optimizes the score of all snippets, not just the top ones, as shown in this two example. With our recursive mapping, this low scoring abnormal snippets can get higher scores like this. While the high scoring normal snippets can be adjusted lower like this. So our method improve our overall detection accuracy. And the second challenge is privacy and making VD work across many different real-world environments. Currently, most weekly supervised video and reaction models use a one-size-fits-all approach. They train a single model to handle many different diverse things, but in reality, surveillance data is managed by different organizations, and the privacy rules make it difficult to share data between them. This is not only limits our ability to build truly general models, but also reduce how well these models perform in real application. Another challenge is that the definition of an anomaly can vary from scene to scene. For example, riding a bike may be normal on the road, but forbidden in some part of the school. Training a centralized one-size-fits-all model can lead to label inconsistency for similar activities in different environments. All of these challenges make it hard to develop robust and practical models for real-world use. To address this, we introduce an adaptive local model regression algorithm. Federated learning is a great fit for a VD problem because it solves both privacy concerns and the challenge of label heterogeneity across scenes. The last challenge is that most general VD method context agnostic. Training private weakly supervised VD method model across multiple screens is not easy. Currently, most weakly supervised VD methods are context agnostic. Like this example, they use a task agnostic pre-trained facial structures, usually trained on action recognition dataset to extract the feature from video snippets and learn an anomaly ranking model. However, using these pre-trained backbones for different things can introduce domain gaps. Action recognition datasets typically contain only one person per video, while video often involve multiple people and more complex events. Some events in video may actually be combinations of several actions make feature representation less accuracy. And real-world surveillance video are highly diverse. They have different the different things can vary in structure, lighting, resolution, and frame rate. So the context agnostic method reduce the model robustness and often miss subtle anomalies. If local models are not well trained due to thin heterogeneity, their errors can negatively impact the aggregated global model and even propagate through the entire network. To address this, we introduce a thin similarity selection method by aggregating my models only from similar things. We reduce feature heterogeneity between things and limit the spread of errors across the network. As you can see in this framework, we first use a pre-trained video MAE backbone to extract features from the video. The original feature has 1,408 channels. To improve computational efficiency, we compress this feature in two ways. First, we calculate the average across all channels. Second, we compute the max average and standard deviation across the channels. These two types of features are often used as inputs for two different detectors in our model. The channel average anomaly detector outputs a decision parameter alpha and a CAD score. The channel statistical anomaly detector outputs a detection parameter beta and a CSAD score. To solve the discrete optimization problem, we design a novel mapping function. The input are given a score and a decision parameter. This function maps the input to a refined output score. You can see the visualization of this finger. The x-axis is the input score and the y-axis is the output score, and the different lines represent the different values of the decision parameter. For example, if the input score is this and the decision parameter lines are this. So we can get the output score be lower. It could be this. So we can use this function to re-optimize the anomaly score, and then first we apply this mapping to the duty data scores using the detection parameter alpha. Because alpha comes from the average feature, it helps reduce sensitivity to feature noise and improve the robustness of the model. Next, we use the detection parameter beta to map the value from the statistical feature, which capture temporal correlations between video snippets and refine the detection boundaries for smoother transitions. Finally, the outputs of both detectors are multiplied together to produce the final anomaly score. The core idea of scene similarity adaptation local aggregation is to consider both the local model and the global model, allowing each client to adaptively update its private model weights based on its own data distribution. To achieve this, we introduced two adaptive weights metrics to balance the contribution of the local and global models. We also propose selective aggregations method that aggregates clean models based on scene similarity. Each client's first train its local model, then based on the SSIM scores between scenes, each client selects the k most similar models from other clients. These selected models are aggregated from a personalized global model, which is then returned to the selected clients. To support adaptive local aggregation, we treat the aggregation process as an optimization problem. The goal to minimize a local loss function, which takes as input local model, global model, and local data. Here the global model weights and local data are fixed. The only learnable parameters are two adaptive metrics donated as A and W, which are used to update the local model weights in that step. For a local model configuration leads to a lower loss, we consider it be it's a better fit for that specific client. So we use gradient descent to minimize the loss and update A and W accordingly. To ensure convergency, we monitor the last five loss values. When the standard deviation of these values falls below 0.1, we stop the optimization. By doing this, we can train a personalized and context-dependent local model for each client in the weighted task. All right, now let's take a look at our experimental setup and the results. We used two multi-scene datasets, Tianjin type and using normal. These datasets will help us simulate real-world environments where each scene is treated as a separate client. For our experiment, we deploy each device in JSON AGX area as the client. We use a Flower framework to manage federated learning across these devices. to evaluate the performance, we use the AUC ROC as the main metrics, and also measured the false alarm rate to check how robust our model is. We can say from the results on Shanghai type and normal that our model outperforms the baseline models. It achieves higher detection performance and lower false alarm rate. Here are some visualizations of our anomaly scores on simple videos. The blue lines shows the score from our model, and the green lines shows the baseline results. As you can see, our model produce robust results for both abnormal videos and the normal videos. Here are some interesting experimental setups. In first table, we evaluate the effectiveness of each component of our framework on ShareType. You can see that when we use all components together with SSLA algorithm, we achieve the best performance. In contrast, if we only use the Fed average, the performance is lower. This is Fed average performance. The second table shows cross dataset evaluation. We use PAD2 and Avenue, which are single sync datasets with different type of anomalous resolutions and frame rates. Each dataset is deployed on a separate client. Our SSLA algorithm achieves the best performance and the lowest false alarm rate compared with the other method. In the final table, we test the framework's ability to handle label heterogeneity. We define the reading bicycle events as normal in scene 4, 6, 10, 11, and 12 of the ShareType datasets, while keeping the other scene unchanged. We compare the baseline centralized model and our model. The first row shows the original result. The second row shows the results with redefined labels, and the last row shows the change in AUC scores. We can see that our method effectively handles label heterogeneity and can adopt to scene-specific anomalous definition. Besides performance, inference efficiency is also important for real-world VAD applications, especially on each device with limited computational resource. We evaluate both facial extraction time and the model inference time during the inference phase. We found the facial extractions is the main limitation factor for real-time performance. To address this, we applied pruning and personalization to video and V2 model. Then we evaluated both speed and the accuracy with a pruning rate of 30%. We were able to speed up the model significantly while still maintaining high accuracy. And thanks for your attention. If you have any questions, you can reach out to me by email or on LinkedIn. For more details, please check out our paper or the code. Thanks again for the attention, and see you next time.
Oops. Okay, this was a bit of an abrupt ending. Let me share again the last few seconds of the video so you can see the contact details. Yeah, I think this was a super interesting work. It's the first time I see this type of work in the context of FL, where seeing similarity is a very big challenge. I think also one of the things I really like was that it's actually running on edge devices like NVIDIA Jetsons, and the results look pretty strong, especially when using the proposed SSALA strategy. So be sure to reach out to Jiahang Li for more details if you are curious about this type of work, and also check the paper on the repo. I saw his repo a while ago and I was really impressed about it. Okay, so let's wrap up the Flower Monthly. So this was the talk, Federated Weekly Supervised Video Anomaly Detection by Jiahang Li. And this is the second talk for today. So with this, we are wrapping up the Flower Monthly for the month of October. The next monthly will be the first Wednesday of November, which is the 5th of November. I think in the meantime, I encourage you to take a look at the updated Flower documentations, in particular to the tutorials. Reach out to Jiahang Li or Fran if you're interested in their work that we got to learn more about today. And see you in the next Flower Monthly. Bye.